We are starting a new section on estimation and A/B testing. In the last section, we talked about how to use random variables and probability distribution functions associated with those variables to talk about uncertain events. We did learn some formulas for the joint and conditional probabilities. The more important one was the Bayes rule. We applied it in multiple contexts. And in this section, we will learn how to estimate parameters of the models. When we talked about fitting distributions into the data, we talked about three specific distributions: Poisson, binomial, and normal. But we never really talked about how to calculate parameters of those distributions, especially for the normal one, how to calculate mu and standard deviation given the data set. So we'll talk about this in this section. And then we will start using the normal distribution for hypothesis testing and confidence interval estimation. And the application of hypothesis testing will be A/B testing. We will use R as we did in the previous section, and I encourage all of you to exercise R as much as possible. Although MATLAB or Excel are pretty popular among data analysts, are becoming by default a standard tool in many of the shops that do data analysis. Even if you're not a data analyst and you will do it on occasionally, R is relatively easy to use and learn for you to pick up. Some links on the R resources and standard commands, which we're going to talk about throughout the course. So let's talk about the technical part of these sections. So we're going to talk about return on the stock again. We talked about return on S&P 500 and we analyzed data from the crash. And one of the conclusions we made that using normal distribution to model returns of a financial asset like an index fund or a specific stock is probably not that great of an idea, because the normal distribution does not capture what is called tail behavior. Something doesn't capture those outliers on the right hand side and left hand side, doesn't capture the crashes on the left hand side or some unusual good days on the right hand side. But for modeling the normal day, normal distribution is actually not that bad of a model, and we will stick using the normal distribution, always keeping in mind that it works for normal days. It doesn't really work very well for unusual days. So let's X be the daily returns for Google. And we assume that returns are independent of each other and they follow normal distribution. The question is, a normal distribution has two parameters: the mean, mu, and the standard deviation, sigma, or variance, which is sigma squared. The question is how to find those values mu and sigma. Again, we assume that we just observe independent random sample from this normal distribution. And so each of the observations, each of the daily returns come from the same distribution. So it's one distribution that describes the returns on any of the given days. Then we're simply going to use sample mean and variance to estimate the mean and standard deviation of the variance of the distribution. So we're going to call it x bar. X bar is just the average across the returns observed in our data set, where n is the number of the observations. And we're going to say that x bar is the estimate of the true mean mu. So we don't really know what is the true mean. The reason we don't know because we don't know what's going to happen in the future. In the future, things might change and the returns might start to look slightly different. So the true mean of the distribution is not known to us, so we're gonna just use the estimate. Another good example why we don't say it's a mean, but it's an estimate of the mean is, let's say you want to estimate average weight of a person in United States. So you try to analyze the overweight problem in the country, and you try to see what's the average and what's the deviation from the average. Now you cannot really measure the weight of every person in the United States. You can only measure subsample of those people. So you don't really know the true average. You have some estimate of this true average based on the sample. So the same thing here. We don't really know what's the true behavior of the Google stock. We just observed returns so far, and we can only judge what was the mean up to this point. And now the variance estimate S squared is just the average across the deviations between the observed return. So this is observed returns and the average return. And we take the deviations, we square them, and then we take an average across all of those squared deviations. Now I have n minus 1 here. This is statistical, you can call it an artifact. It's the true standard deviation is the reason we have n minus 1 here, because we already used n observations to calculate this x bar here. So we're kind of recycling the data twice, and in order to adjust for this fact that we are recycling the data, we put n minus 1 here. But for all practical purposes, you can put 1 over n here, especially when you deal with large enough data sets, and in a lot of the cases, you will see in this class and in your professional life, the sample size is going to be large. And so by large I mean n is, so when n is greater or equal than, let's say, 30, you can instead of 1 and minus 1, you can write 1 over n. So it doesn't really change the number that much. All right, so that's how we get the estimates. And what you see here on the left hand side, you see the prices of the Google return from 2005 to 2020, and then I calculate daily returns for each of the days, and I plot the histogram. I calculate it in percentages. So I plot the histogram, and you see the histogram actually does remind us of a bell curve. So if you think of fitting a normal distribution into this data set, so I think normal distributions should do a relatively good job estimating this data set. So the mean is close to 0, which we expect, right? So on average, sometimes stock goes up, sometimes stock goes down, and on average it's close to 0. There is small non-zero value here, which is positive actually for the Google stock. You can just say it by looking at the price, that the price moves in the positive direction, so the average return is still positive, although sometimes it goes up, sometimes it goes down. Okay, so now once we know how to estimate the parameters of the normal distribution, and we know that we're going to use normal distribution model to describe the returns of the Google stock, now I assume that I invest all of my money into Google. And I would like to know the following. I would like to know what is the expected return over 1 year for this investment. And what about the risk? What about the volatility? How much money I'm potentially going to lose investing into the Google stock? And the third question is, what is the probability that I will lose at least 3% in a day? Let's say I'm a risk-averse person. I lose my sleep if I lose more than 3% in a given day. And when I invest into something, I need to know what are the chances of this happening and how many nights I potentially will go sleepless. Okay, so let's do calculations and answer those questions. We're gonna calculate the mean and standard deviation for the returns. What you see here are the outputs from R. I took actual data set that you saw the plot of and calculate the returns. So you see it's slightly positive, as we expect. Google is a good company, so the returns on a daily basis above 0, but it's close to 0. And we also calculate standard deviation around roughly 10 cents. Okay. And now, if we want to calculate the annual expected return of this portfolio, there are 252 trading days in a year. So I take the daily return, multiply by 252, and I get 17.8%. So this is not that bad. This is my expected yearly return on the Google stock. And the risk or the volatility is the same thing. We just take, so the risk is 1.86% in a given day. Okay. So again, if you remember, if we use the normal distribution, so here we assume that my returns follow normal distribution with mu of well, I just gonna say mu and sigma squared. So that's my mu, and that's my sigma. Then you remember that with 95% chance, the variable x gonna be in the interval mu minus 1.96 sigma 1 mu plus 1.96 sigma. Okay. So now another thing I can say that in 95% of the chances my daily return is going to be in this specific interval. Anyhow, let's calculate the potential possibility of losing money. So I'm gonna standardize things, and I'm gonna calculate. You remember, I want to know what's the chances of losing 3% in a given day. So I'm gonna calculate difference between 3%, the number I'm interested in, and the average return. So that's the difference, and then I'm gonna put it onto the standard deviation scale. So minus 1.65. So that's the number of standard deviations. 0.03 is away from the average return. So it's relatively low probability event, and if you calculate the probability of it, so we want to calculate the probability that my random variable is going to be less or equal than minus 0.03. So it's just the p-norm function, and for the standard norm, so remember we standardized the random variable here, so we want to know what's the p-norm. So here we're calculating probability that z is less or equal than 1 minus 6.5. So instead of using the original random variable x, I use my standardized version of it z, and I get this 0.049. So roughly 5% chance I can lose at least 3% in one day according to my normal model.